Here is a video on how to think about expected utility visually. Most textbooks that talk about expected utility show you a concave function with 2 points on it that are connected with a line. I want to briefly explain why they do this in a bit more detail. Now first, what is a concave function? A concave function is a function that, if you take 2 points on the function and connect them with a line, the whole line will lie below the function. So just like in the example here. Another way to identify a concave function is by looking at the second derivative. Where the second derivative is negative, the function is concave. A concave function is always linked to a certain risk attitude, namely risk aversion. The other type of risk attitude, risk seeking, belongs to convex utility functions. As you can imagine, a convex function is the opposite of a concave function. If you take 2 points on a convex function and connect them with a line, the line will always lie above the function. If you already understand how concavity and convexity relate to risk aversion and risk seeking respectively, then this video is not really for you. However, if you still have a bit of uncertainty, I'll try to explain it a bit more by focusing on risk aversion. The case for risk seeking should become automatically clear if you understand the case for risk aversion. So here we look at another concave utility function. Let's say we look at 2 options, option A and option B. Option B is preferred to option A. Why? Because option B yields a higher utility than option A. Now any option that lies between A and B can be expressed as a linear combination of A and B. So meaning we multiply A with P and multiply B with 1 minus P, and then with P being between 0 and 1, we get a point between A and B. For example, if A is 1 and B is 9 and P is 0.5, then the combination here P times A plus 1 minus P times B would be 5. In fact, in the example that I've drawn here, P is indeed 0.5. From the graph we can also infer the utility of the combination of A and B, so in our case here the utility of 5. As you can see, the difference between the utility of A and the combination, so the difference between the utility of 1 and 5, is larger than the difference between the combination and B, so here in our example the difference between the utility of 5 and the utility of 9, even though the difference between 1 and 5 and 9 is in both cases 4. This is called diminishing sensitivity. As your options become more valuable, the same difference means less and less. This is usually a quite reasonable assumption because, as you can imagine, if a person who owns hardly any money gets £100, he or she will derive a huge amount of utility from it. However, if a millionaire gets another £100, it probably doesn't mean that much to him or her. Alright, so how does this relate to expected utility? And why do we combine the 2 points with a line? The reason is the following. The line gives us the utility of a gamble that combines A and B, whereas the red line gives us the utility of an option, the black line gives us the utility of a lottery combining A and B. So here, as we can see, the utility of the lottery that gives you A with probability P and B with probability 1 minus P lies below the utility of getting the combination of A and B directly. So in our example, this means that the utility of 5 lies above the utility of a gamble that gives you 1 with probability 50% and 9 with probability 50%. And since this is a concave function, and for a concave function the line between 2 points always lies below the function, this is true for every possible lottery we can create using 2 options. Yes, so once again, if this is a concave function, the line will always lie below the function, and therefore the utility of a gamble of A and B will always be below getting the combination of A and B directly. Now obviously, where exactly on the line you are depends on what the probabilities P and 1 minus P are. The line does not only show us the utility of the gamble, it also visualizes the gamble itself, because the point of the lottery also represents the probabilities of the gamble. What do I mean by that? The distance that we travel from A to the point of the lottery is exactly the probability of B, and the remaining distance from the lottery to B is the probability of A. So here in this case, when both the probability for A and the probability for B are 50%. This is not so clear to see, so we look at a different example. So here in this example, the probability for A is 75% and the probability for B is 25%. So for example, if A is still 1 and B is still 9, then the combination here is 3. So we already know that the utility of the gamble that gives you A with 75% probability and B with 25% probability is going to be lower than if you get 3 directly. However, I also want to illustrate how the probabilities tell you how much of the line you need to travel. Here you see the distance from A to the point of the lottery is exactly 25% of the line, the probability of B, and the distance from the point of the lottery to point B is the probability of A, so here 75%. So this is how you visualize a lottery in a utility function. Let's make use of what we just learned in an example. So assume we have a decision maker that is risk-seeking. As we have established earlier, a risk-seeking decision maker has a convex utility function, which is the case here. Which lottery does a risk-seeking decision maker prefer? Does the decision maker prefer L1 over L2? And does he or she prefer L1 over L3? Now some people think that being risk-seeking means you like risk just for the sake of it, but that is not true. If you compare L1 and L2, you see that they have the same outcomes, but L1 gives the better outcome with a higher probability, and therefore even a risk-seeking decision maker is going to prefer L1. Similarly, if you compare L1 and L3, you see that they have the same probabilities for the good and the bad outcome. They also have an identical good outcome, but the bad outcome is worse in L3 than in L1. Therefore, again, L1 dominates L3, and even a risk-seeking decision maker is going to prefer L1 over L3. Now we also want to show this graphically. This is the representation of L1, a combination of 50% 20 and 50% 100. As we can see, the decision maker is risk-seeking, so the utility of the lottery always lies above the utility of getting the combination directly. If we now draw L2 into the same graph, we see that the utility of L2 must lie below the utility of L1. Both L1 and L2 lie on the same line, because both are combinations of getting 20 and 100. However, in L2, we only travel up 40% of the line, the probability of the good outcome, whereas in L1 we travel up 50% of the line. So L1 truly dominates L2. So to sum up, Lottery 2 lies further down on the same line, so it must be worse than Lottery 1. How about Lottery 3? Lottery 3 lies on a different line, the combination of 0 and 100. However, we can still be sure that the blue line here is going to always lie below the purple one, meaning that L3 is always dominated by L1. Why is that? It is because in both cases we travel up exactly 50% of the line, because in both cases you get the good and the bad outcome with 50%. However, both lines end at the same point, but they do not start at the same point. L3 starts further down, so if in both cases you only move up 50% of the line, then you will reach a lower point if your starting point is also further down. So as long as the probabilities are the same and the good outcome is the same, if the bad outcome is worse, it will definitely give you a lower expected utility. So to sum up, both L1 and L3 lie exactly halfway on their lines. The lines have the same endpoint, but the line of L3 starts further down, so L3 must be worse than L1. Alright, I hope this video helped your intuition about expected utility.